Welcome to chemistry class. Let us learn about the crystal field theory under the topic coordination chemistry and organometallics. So crystal field theory was proposed by H. Bath and Van Vleck, and it was originally applied to ionic crystals. Okay, so what was that compound to which originally the crystal field theory was applied? That was ionic crystal. So why was this used? So the crystal field theory was applied to the ionic crystals to explain the optical properties, and therefore it was called crystal field theory. However, this theory was applied to the study of coordination compounds in the year 1950. Okay, so the valence bond theory that was earlier suggested represented the ligand metal bond as covalent. What was the bond between the ligand and the metal? That was covalent. Okay. So covalent means there was an electron pair that was being shared between the metal and the ligand. So it was used frequently, but it is not adequate to explain the properties of complexes such as the color and the magnetism. So currently the bonding in coordination complex is usually described by the crystal field theory. This is the crystal field theory that is usually used for understanding the color and the magnetism in the crystal compounds, or you can say the coordination compounds. Fine. So this theory accounts for more satisfactory explanation for the properties of complexes, especially the color and the magnetism. Now let us learn the main points of the theory. Okay. So what's the first point in the crystal field theory? According to the crystal field theory, bonding in complex ion is completely electrostatic. Fine. So electrostatic means there are positive and negative charges. So this theory regards the ligand atoms of ionic ligands such as fluoride, chloride, cyanide as negative point charges. As negative point charges. Fine. And if the ligand molecules are present as neutral, then they are regarded as point dipoles. For example, ammonia molecule. This acts as a ligand and it has a lone pair and it is a completely neutral molecule. So this is the point dipole. Fine. So what we have understood as the first point of crystal field theory, the bonding is completely electrostatic and the theory regards the ligand as the negative point charges and the point dipoles. Fine. Next, second point in this is the complex is regarded as a combination of central metal ion surrounded by ligands. Fine. Which act as the point charge or point dipoles. The arrangement of ligands around the central metal ion is such that the repulsion between these negative points or dipoles is minimum. What does this mean? This means that the ligands contain electron pairs. Fine. So the ligands are arranged around the metal atoms in such a way so that there is minimum repulsion between the electron pairs present in the ligand molecule or the ligand atom or ion. So the third point here for the crystal field theory is about the interactions. Interaction between the positively charged nucleus of the central metal ion or atom and the negatively charged ligands. Okay, positively charged metal atom and negatively charged ligands. So there are two types of interactions. First interaction present is the attractive force. Okay, the attractive forces arise due to the positive metal atom and the negatively charged ligands or the negative end of a polar neutral molecule. For example, in the case of the complex FeCN6 with the charge 3-. Okay. So here the interactions between the Fe+3 ion, that is the metal ion, and the negatively charged cyanide ions, there is attraction. Fine. Whereas in the complex Cr(NH3)6 with the complete oxidation here written here is +3. So the interactions between here the chromide ion, this Cr+3 ion, and ammonia molecule, this is a neutral molecule, fine, there is attraction. So these attractive forces bind the ligands to the metal ion. The bonds between the metal and the surrounding ligands are purely ionic. Okay. So this theory does not consider the orbital overlapping. Now let us see the second interaction present between the metal and the ligand. Okay. The second interaction is the repulsive forces. The repulsive forces arise between the lone pairs of the ligands. Okay, the lone pairs of the ligands and the electrons that are present in the d orbitals of the metal ion. Okay, so the crystal field theory mainly focuses on these repulsive forces. The forces are responsible for causing a considerable effect on the relative energies of the d orbitals of the central metal atom or ion. Now, the fourth point according to the crystal field theory says that in a transition metal atom or ion, okay, there are 5 d orbitals. How many d orbitals? 5 d orbitals, which are designated as dxy, dyz, dzx, dx square minus y square, and dz square. So these 5 d orbitals are divided into 2 sets. How many sets? 2 sets, depending on the nature of their orientation in space. So the 2 sets here we have dxy, dyz, dzx, which orient in the region between the coordinate axes are designated as what? T2G orbitals, and this is pronounced as T2G. Okay, so these T2G orbitals are 3-fold degenerate, and these are the non-axial orbitals. Fine. And the other set, dx square minus y square and dz square, these orient along the axis, and they are called as EG, pronounced as EG. These are 2-fold degenerate, and these are called the axial orbitals. Okay, so dxy, dyz, dzx, these are the 3-fold degenerate orbitals called the non-axial orbitals. Okay, and dx square minus y square and dz square, these are the EG orbitals and called as the axial orbitals. So in a free transition metal atom or ion, all the 5 d orbitals have the same energy. They have what? They have the same energy. That is, they are degenerate. You understood the meaning of degenerate? Degenerate means all these orbitals, they have the equal energy, they have the same energy. Okay, so however, when the ligands approach the metal ion or atom, the electrons of the d orbitals of the central metal ion or atom are repelled by the lone pair of electrons of the ligands. So what happens? As a result of these interactions, the degeneracy of the d orbitals of the metal ion is lost depending on the orientation of ligands in space. The d orbitals, they split into two sets of orbitals, okay, having different energies. This is called crystal field theory. It is the basis of crystal field theory. Okay, so the degeneracy of the d orbitals, the metal ion lose their energies, they become in the different energy levels, and the d orbitals split into two sets of orbitals, they have the different energies. This is called the crystal field splitting, and the theory has this basis. So the extent of splitting depends on the number of ligands and the position around the central metal ion. The splitting is different in different structures with different coordination numbers. Fine. So today we have learnt about the main features of the crystal field theory for the topic coordination and the organometallics. Fine. So to learn more about the chemistry topics and to understand more chemistry, just like, visit, share and subscribe chemistry class. Thank you.